So good morning, guys. Today I am back again with the discussion of today's LeetCode weekly contest 347. So if we talk about today's problem or today's contest, then it was not, of course, a good contest for me because I took way more time to solve the easier problems and I could not solve the harder problem. So of course that's a downfall for me. And yeah, I came up with a solution for question fourth and passed more than half of the test cases, but still the problem remained unsolved. So yeah, it was not a good contest for me, but I hope to improve and get a better rank in the next contest. Yeah, we never lose. We just keep on learning and performing better. Yeah. So let's start with the first question. So in the first question, what it says that we are given a number. We just have to remove the trailing zeros from the end and then return the final string. So if we have this string, let's say 5123 5123 0100, so we have to keep on removing the zeros from the end, and the final result we get is this 512301 512301. So simply we'll have the string, we'll keep on removing the last characters from the end and just return the final string. So now pretty straightforward. So basically we have assigned temp as string, and while since and we have used this condition, like if with temp dot back we get the last element of any string. If it is equal to 0, we keep on popping the last element and then we return temp. Like no need to return temp. We can simply use without any temp, we could use temp, we could use num also. Why take some extra space? So let's let it be num. Yeah, so this will also work. So let's give it a try. Of course it will work. Yeah, so this is pretty much the solution, nothing to explain here. Like yeah, so let's move to the next problem. So in this next problem, I'll basically explain what the question is asking us to find. The problem statement is like quite big and it's of like no use as such. So yeah, let me zoom it a bit. Yeah. So what we have to do in this problem, like it is not working, I think. Yeah, so no worries. Like okay, so what we have been given is like we have been given a matrix of m cross n size, and for each element, like if we have 1 2 3 1 2 3 3 1 5 3 2 and 1. Let's say let's not take let's take a larger array, like 4 ones. Like let's take this example only. So in this, what we have to do is for each element, like if we take, like let's take a bigger example, 4 7 1 6 5 4 3 1 6 6 7 9 7 1 6 3. Like, so if we consider this type of an array or a matrix, so what we have to do is for any element, let's say I take this element 2. So this 2 belongs to this particular diagonal, this 2 belongs to this particular diagonal. Like if we take this 7, this 7 belongs to this particular diagonal. If I take this 1, this 1 belongs to this particular diagonal. So what we have to do is, like if we take if we take this element, then we'll consider its diagonal, which is this, and we'll break it into two halves. Like let's take a different color, let's say white. So we'll break it into two halves. First half will be the upper half, this portion. West will be the upper half, which is this portion, and then will be the lower half, which is this portion. So if we take the top left portion, top left basically, the top left basically includes all the elements above 2 in this direction. So it is only 3. And if we take the bottom right, in bottom right we'll have these two elements, 6 and 6. The 6 and 6, we have these two elements. So for any particular element, we'll just consider to which diagonal it belongs to, and all the elements accepting that in the above portion falls in the TL range, and all the elements below that particular element falls in the BR range. So we have this. The number of unique elements in TL is 1. Number of unique elements in 6 is 1. So we have to, the answer of I comma j will be the absolute difference of both these, which comes out to be 0. So in this case, this problem, this is how the problem needs to be solved. And yeah, so like if we consider this example, the 1 2 3, yeah, so yeah, so simply the how this solution came, like 1 2 3 3 1 5 and 3 2 1. So if we store the answer here, so we'll see that for this particular element, nothing lies above its diagonal and below its diagonal, so answer will be 0. It is 0. For this particular element has only 3 in the top left and nothing in the bottom right. So it will be number of unique elements in top left is 1, number of unique elements in bottom right is nil. For 1 also, it has 2 elements in the top left and both are 1, so number of distinct element is 1, and below it there is none, so it is 0, so basically it becomes 1, and so on. We'll get the other elements also. Yeah, so simple, so approach is simple. For we'll take particular element, we'll take, like in this example, we'll take a particular element, keep our I and j pointer here, and we'll take 2 pointers a and b, and we will keep on decreasing a and b both by 1, because if we are consider a diagonal, then we'll keep on decreasing the 2 pointers a and b both by 1, and we'll keep on moving in this direction and store a set to store the number of unique elements. Similarly, then we'll take 2 pointers a and b and keep on incrementing both of them simultaneously and store them in the set. So number of unique elements in the set and their absolute difference will give the answer for the I comma jth element. So the solution is pretty much simple. We'll declare an answer array, a matrix. For each element, what we'll take upper as one of the set and lower as one of the set. Upper will store all the elements in the top left basically upper set will store all the elements which lie in the upper left diagonal of the current element, and lower will store all the distinct elements which lie in the bottom right diagonal of the current element. So we'll take 2 pointers a and we'll keep on decrementing it, and keep on inserting that element in the set, and then we'll act for the so this is for this is basically for the top left diagonal, and this is for the bottom right diagonal, and we'll keep on inserting it, and then answer will be the absolute difference of the number of the distinct elements in both minus their absolute difference. Yeah, so we'll get the final answer. So this is pretty much straightforward. Yeah, then we'll move to the third problem. In the third problem, what is being asked, let me erase this. Yeah, yeah. So in a third problem, what we have to do is basically we are given a particular string. Let's say we are given any string, and we can perform 2 types of operation. Let's say I've been given a string 0 1 0 1 0 1. So we can perform 2 types of operations on this particular string. Like if we choose the ith element, let's say if we choose an ith element, then we can invert either all the bits in this region, or we can invert all the bits in this region. And the cost for inverting bits in range from 0 to I is basically the length, or if we take from I to n minus 1, then the cost is 4. So basically inverting all the bits is basically has a cost which is equal to the length of all the bits that we are currently changing. This is the first type of operation in which we take the ith index and invert all the bits from 0 to I, from the range of 0 to I. And the other type of operation is basically inverting all the bits from I to n minus 1, and the cost is basically the length. Like if it has length 4, it has length 2. So we have to make all the characters of the string equal. So so how can we approach this problem? Like so what can be the approach for solving this type of problem? So we should first notice that we are given a binary string, and now if we are binary string, it will always have either 0 or 1. These 2 characters are possible, and then we have to return the minimum cost to make all the characters of the string equal. Now we have to make all the characters of the string equal, so there can be 2 possibilities. Either all characters will be 0 or all characters will be 1. So there are two possibilities. Like the way I approached this problem is of course not the most optimal one, because during the contest this was the first thing that I came to my mind. If I'll of course read the editorial also, and if I'll find something more optimal, of course there is, I saw other people's solution also, so we'll definitely tell you, or you can watch some other people's other creators video, as they would have provided better solution. But this was my intuition of how did I solve the problem. And so basically, I consider it like we try to convert this into two types. Either we can convert it into all zeros, or we can convert it into all ones. 1 2 3 4 5 6. Okay, so what did I consider in the contest was, let's say we convert them to all zeros. Let's say we convert them to all zeros. Okay. Let's say we convert them to all zeros. 1 2 3 4 5 6. Okay, so what we have basically done is like we have the string 0 1 0 1 0 and 1. So now we have to choose the indices optimally. Now I thought of using recursion, but of course recursion won't work here, because for any particular state we have to invert all the characters. So that's of course a tedious task which recursion could not handle properly. So I thought we could of course use greedily. And then the first thing that struck my mind was basically we try to basically act optimally and start from the middle of the string. So we try to make all the elements equal. So we start from the middle of the string. Like we have these two characters, let's say these are our middle two characters. We try to make them equal and then go in the left or right region. So we maintain two pointers, I pointer and the jth pointer, and we see that if we have to make all of them equal to 0, so we see that here I and j, and also we'll maintain we'll also maintain two variables, CL, which is equal to 0, and CR, which is equal to 0. CL and CR are basically tells what will be our current status of the bit after inversions. Like if I'll tell you through an example. So if we see that I and j here are, so we are trying to make all of them to 0. So what we've done is we see that I and j are not equal to 0. So we'll try to make this one to a 0. But if we have to do it, we have to perform the second type of operation, and so we have to invert all the bits here. And since we have to invert all the bits here, so after this the string would become 0 1 0. The string would become 0 1 0 0 1 0. So this got inverted, and because of this these two characters got same equal. And so since we have changed the right portion of the string, we'll increment CR by 1. So this shows that because it is just like the concept of lazy propagations in segmentary. We don't actually make the changes, but we remember the changes that we have made, so that we could reach to a final state. Like we have increased CR to 1. It means that all the bits are now will be changed by 1, or one time of one inversion has been performed. They basically tell the number of inversions in the right region. So one inversion has been made, so all the states of the string will now be 1 increased. So it will be equal to 0, it will be equal to 1, it will be equal to 0. So in this way. So now we move our I to left and j to our right. We see that both 1 and 1 are equal, but we have to make them both equal to 0. So we have to invert this portion also and this portion also. Because of this, these two will become 0. So now our string will become, we have to invert this portion, so 1 0 0 0, and invert this portion 0 and 1. And so now these two characters are also equal, these two characters are also equal, these two characters are also equal. So so in this case we incurred a cost which was basically which was basically n minus j, and in this case our cost was 2 times of I plus 1, 2 times of I plus 1, 2 times of I plus 1. And in this case now we move our I here and j here. We again see that both 1 and 1 are equal, so we have to invert this particular portion and this particular portion. So again now our string will become 0 0 0 0 0 and 0. And so we have to incur a cost which is 2 times of I plus 1, which is 2 times of I plus 1. Here it is 0 plus 1, it basically 2, and it is basically 0 1 2 4, and here it is basically 0 1 2 3. 6 minus 3 3, so 3 plus 4 plus 2, so 3 plus 4 plus 2, so the answer is 9. So this is one possible scenario. So if we are at the ith bit and the jth bit, so either both can be 0, basically we're considering if all are zeros. If we are considering the case 1, if we are considering the case 1 that all are zeros, so in that case if both are 0, the cost will be 0 and we'll move to the left and right. If it is 0 1, so we'll invert this particular portion. If it is 1 0, we'll invert this particular portion, and if it is 1 1, we'll invert both the portions. And same goes with by converting all of them to 1 and then take the minimum answer. So this is what we have basically done. Of course, it's a very tedious and like not an interview centric code, but this was the first thing that has struck my mind and will definitely improve upon it. And so what we have done is basically we have maintained two answers. Answer 1, if we make all the characters to 0, and answer 2, if we make all the characters to 1. So we have basically set the I and j pointer at the middle elements of the elements, and we have maintained CL and CR. They basically tell the number of inversions, number of lazy inversions that we will make in the future, yeah. So basically we have considered like if the number of inversions, if we are at the current I and jth character, if the number of inversions are odd, if in the left side the number of inversions are odd, it means that we have changed the bit odd number of times. And if we change, let's say we have 0, and if we basically invert 0 odd number of times, let's say 3 times, let's say 1 time or 3 times or 5 times, will end up being finally inverted. But if we have any bit and we change it to even number of times, 2 and 4 times, it remains 0. So what we have basically done is, if in the left side the number of the number of inversions that we have done is odd, then we'll change it 1 to 0 and 0 to 1, and same goes for right. And if both are 0, we'll simply decrement I and increment j. And if both are equal to 1, then answer will be 2 times, because we perform both type of operations simultaneously and increase both of them. If temp of I left part is 1, then we'll perform inversions on left, else we'll perform inversions on right, and then go left and right. And same we'll perform then we'll perform the same thing for 1. Then you can perform the same thing for 1. Convert all the bits to 0, convert all the bits to 1, sorry, and we'll perform the same thing, and then we'll take the minimum answer. So this was the code for the third problem, and now let's move to the final problem. Yeah, so in the final problem, let me explain this problem. So basically what is in this problem is like, let me erase this first. Let me add a new slide to it. So what we have to basically do in this question is, we'll be given, let's say, any metrics. Let's say we are given 3, 1, 6, and minus 9, 5, and 7. 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 Yeah. So what we have to basically do in this problem is, we can start from any cell as we want. And we can from any cell, we can jump to any particular cell in the same column, up or down, or in the same row, left or right. But from jumping from ith element to jth element, a of I should be strictly less than a of j. So we should always jump to element which has a value which is strictly higher than the current element. So we have to find what is the maximum number of cells that we can visit by maintaining this particular condition. Okay. So if it would have been like jumping to adjacent elements, then it would have been an easier problem. But what I thought, I'll tell you what was my approach in solving the problem. And I think most of my approach was wrong, but it was passing major of the test cases. So as you can see that it was my code, it passed 325 test cases in 564. Of course, that's almost half. Of course, that's a wrong approach. But yeah, I think my code was a bit tedious, I must say, or lengthy, but yeah, it is what it is. And yeah, let me explain what I did. I'll definitely get change upon my approach, and will let you know the solution also. And so what we have basically done is, what was my approach in the contest? My approach was like so what was my approach? That I saw that if we consider all the elements within a row, like if we consider the elements within the first row, let's say this is the R1 row, this is the R2 row, this is column 1, this is column 2, this is column 3. So if we consider row 1, so it has elements 3, 1, and 6. So if I can jump from any element to any particular other element, if by maintaining the increasing condition, so we can sort it. Like if we sort it, we have 1, 3 and 6. So we can jump from 1 to 3 and then from 3 to 6, and it can be simulated like this. We can jump from 1 to 3 and then we can jump from 3 to 6. So we have maintained all the conditions, and within the row we have jumped also. So we can visit 3 cells at maximum, and same goes for column also. So what I have basically done is so I have sorted all, I have maintained, I have basically sorted all the rows. So basically if I sort the row R1, we get 1, 3 and 6. Let's say like, let me write here. If I sort the row R1, we get 1, 3 and 6. If I sort the row R2, we have -9, 5 and 7. If we sort the column C1, we have -9, 3. If we sort the column C2, we have 1, 5. And if we sort the column C3, we have 6, 7. So what we have done is basically we start from the first element. We start from the first element. And we'll see we can always move either right or down. So basically, see, we have 3. So we find that 3 is in row R1 and in row C1. So we'll locate 3 in R1. So 3 is here, and 3 in C1 is here. So we'll try to find the first element which is greater than this particular element in this particular row and this particular column. So we find that no element is greater than 3 in this particular column, but there is an element 6 which is greater than 3 in this particular row. So we'll jump to this row, we'll jump to 3, we'll jump to 6, then we go to 6. We'll locate the 6 is in row R1 and in column C3. So in R1 it is here, and in column C3 it is here. So we see that in the particular row we cannot find a bigger element than this 6, but we can find a bigger element in the column. So we'll jump to 7. Then we have columns in 7. 7 is in C3 and R2. In R2 7 is here and C3 is here. But we cannot find any element which is greater than R2 or C3 in that particular column or row, so we can't jump anywhere else. So basically we have performed 3 steps. So basically we'll save our answer 3 here because we can visit 3 cells, and we'll also use the concept of DP. How we'll use the concept of DP? Basically I'll tell you, like so what we'll basically do is, like if we are at 3, we see that we can jump, we'll see the first element which is greater in that particular row and column than current element. So we'll use the concept of upper bound. So we'll see if any element is bigger than the current element in this row. Yes, we have 6 first element, and then we'll see any element bigger in the column. So we have none. So we'll go to 6. Then from 6 we'll see any element bigger in the row. No. In the column, yes, 7. So we'll go to we'll go to 7. We'll go to 7, and we cannot find any element bigger. So we have visited one cell here, and when we return, we are basically storing the answer as 1 plus. So for any particular DFS I, we have basically for DP of I, we are basically storing 1 plus the max answer. We come from going in the particular row, column. So like for any element, we'll have 2 options. Either we'll go at a bigger element in the row, in that particular row, or we'll go at a bigger element in the column. So we have some answer, let's say X. We have visited Y cells. So here for this particular cell, the answer will be 1 plus max of X comma Y. Max of X comma Y, and we'll mark it as true, and we'll keep on doing this. So for 3, we find that first element greater in the row is 6. So we go to 6. In the column we can't find. In 6, first element greater than 6 in this column is no one, but in the column it is 7. So we'll go to 7, and we'll keep on marking this as true, and here we'll store the answer as 1. Here the answer will be 2, and here the answer will be 3. So we have used DP so that if we have reached any particular already visited node, so we have already know the answer, that how many steps or cells can we visit from this particular element. Now if we go to the next element as 1, so we know, so if we maintain a DP table, we have some pre-computed answers. Like if we reach this cell, we can at max visit 3 cells. Here we can visit at max 2 cells. Here we can visit at max 1 cell. So if we now consider at 1, now we consider 1. If we are at 1, so we'll see that 1 belongs to this column C2 and row R1. So C2 belongs here and R1 it belongs here. So first element greater than 1 is 3. The first element is greater than 1 is 3 in this particular row, and in the particular column it is 5. So 5. So we have 2 branches, but we don't have to expand 3 again. We'll use DP, and we know that from 3 we can visit at max 3 cells by using this particular column. So we return 3 from here, and from 5 is unvisited, so we'll locate 5. So 5 is in row R2 and in column C2. So we find that nobody is bigger than don't have any element bigger than 5 in the column, but we have in the row as 7. But we already know the answer for 1, so we'll return 1. So here 2 will be stored, and here the answer will be 1 plus max of 3 comma 2. So here it will be 4. So here for 1 the answer will be stored as 4 and it will be marked as true. So in this way, and in the end the array will be filled, and we'll take the maximum of all the elements in this DP table. So this was my approach. So let's tell the solution. So basically first we've constructed a node. Now each node will basically store its value and the x and y coordinate it belongs to. We could of course use a map also, but we didn't use map because there can be if I think like there can be unique elements. No, there can be of course same elements also existing in the array, so we won't use a map for that. Or we can but we can actually by storing the I and jth coordinate or the coordinates of the particular cell as the key and the value as the pair, because the coordinates are always unique for any element in the matrix. So yes, for this we have maintained a node, and then we have defined n and m. We have defined scene as those elements are visited, rs, cs, dp and grid. So what we have basically done here in this case, we have resized this all, and what we have done here is we have gone for each particular row of the matrix, for this row and then for this row, and for each particular row we have pushed all the elements in that particular row into a vector, and then we have sorted the vector. We have then basically sorted the vector. So what it means is that, like if we consider this particular example only, 316 minus 957. So rs will basically sort all these elements. So like we'll sort all the rows. So 136 will be stored like this, 136, and then second row will be sorted minus 9, 5 and 7. And basically each element will itself be basically a node which will store its value, its I coordinate and the jth coordinate. And same goes for cs. Cs will store the columns, so it will become minus 9 comma 3, then it will be 1 comma 5, and then it will be 6 comma 7. So in this way, yeah. So so we have done the same thing here. We have used sorted and we have used lambda function for sorting a custom comparator, you can say. And same goes for the column. We have sorted all the columns, and in each column we have sorted the vector in increasing order of value. After that, we have taken that if we have already seen an element, then we'll do nothing. Then or else we'll call the DFS function for the ith comma j and store the maximum of all the DP values. In DFS function, what we have seen is that if it is already visited, then we'll simply return the answer because DP stores it, hence we'll mark it as true. We'll maintain two rows, current row and current column, and then what does it actually mean? Like if we are standing at particular I comma j, we'll see that to which column it belongs to which column or which row it belongs to. So basically with this we get to know the particular row and the particular column that it belonged to, and then we have made two vectors and pushed both the values into a and b. Then we have applied upper bound on a and b so as to get the first element which is greater than the current element in their particular row and column. And after that, if the indexes are valid, then we have called 1 plus, because the current element plus the maximum plus the DFS function we call from going it to its neighbor, bigger neighbor in the particular row, and same done for find and for going to the neighbor, greater neighbor in that particular column, and then we've returned dp of x answer as this. So of course this approach is of course not correct. I couldn't find the reason for it, but this was my approach, how I approached the problem or did the solution. Yeah, so this was pretty much it, and I passed 325 cases of 564 only. And so this was the whole contest, and yeah, this was the whole contest, how I performed. And yeah, so this is what it is, and we'll try to improve upon it. Till then, stay happy, maintain good mental health. Yeah, till then, goodbye.